chain rule questions. I just want to do one more application. And this is a version of question 15 that you've got. In this particular story that you have got a box. And so I'm going to draw my own version of that because I like to visualize things. So I have a box, looks something like this. Okay, there's my box. And at some certain instant of time, the length is 8, so I'll make this the length. And the width is 3, and the height is also 3. And this box is changing its shape. And the information that they tell me is that its length and width are increasing. And they're increasing at the rate of 4 meters a second. So when you tell me rates and you say the length with respect to t is 8 meters per second, and that the, what was the other one? The width is also increasing, and it's increasing at, in this case, 4. Is that 4 or 8? Let me check. Oh. This is increasing at 4, so is this increasing at 4? And what's the other one? The height, that one is increasing at 8. There, we got it. So the length and width, so the bottom of the box is getting bigger, right? And the height is getting bigger. So it's really just growing in all 3 dimensions. And from this information and this starting point here, we're being asked to find at that one snapshot in time, right, at this point here, with these increases going on, what does the volume of this shape look like? In other words, we're being asked to find the rate of change of the volume with time. And the second one they're asking us is to find the rate of change of the surface area with time. And the third one that they're asking us is to find the length, the rate at which the length of the diagonal is changing through time. Don't know, I'm going to call that D, I think. Right. So first things first, to do question A, since they want to know the rate at which the volume is changing, I need to find a formula using these guys and volume, and that's pretty easy, right? Length times width times height. And now I can find dv by dt. It's a partial derivative of v with respect to L times dl by dt. So it's a chain rule I'm using. Partial derivative of v with respect to w times dw by dt plus the partial derivative of v with respect to height times dh by dt. Are you all comfortable about the chain rule formula that I'm using in this question? Right, now in lots of questions, these are functions of t and we differentiate them, but in this case, everything's a number. So if you differentiate the volume with respect to length, you get WH. The L by dt is 4. If you find the derivative of volume with respect to W, dV by dW, you get LH, also times that number, 4. And if you do this one, you get LW, only times 8. So far, so good. Now, W happens to be a snapshot, happens to be 3. The snapshot height happens to be 3. And the length, that guy's 4. And the length is 8. The height is 3 times 4. And the length is 8. And the width is 3 times 8. And at that point, you basically just grab your calculator and you do 3 times 3 times 4, add 24 times 4, add 24 times 8, and I get 324. Are we good? Any problems with that so far? Right. Now, my box is increasing, so these are positive. Suppose I told you that the height was decreasing, then wouldn't you just put in the negative instead of the positive? So if you're told the height was decreasing at a rate, let's have the width also decreasing. So the length is increasing at 4, the width is decreasing by 4, and the height is decreasing by 8. Wouldn't the only change to my answer be, that's still 4, wouldn't that turn into -4, and wouldn't this one here turn into -8, right? And if I do that calculation, I get 9 times 4, which is what, 36. Take away 24 times 4, can't do that in my head. Take away 24 times 8. And the answer I get in that second situation would be -252. So in my first situation where everything's getting bigger, does it make sense that the volume would be getting bigger through time? In my second story, since 2 of the dimensions are decreasing and only 1 of them is increasing, in this particular case, isn't the volume reducing? Right? At that instant in time, the volume, if you waited 1 second, wouldn't the volume lose -252 cubic feet? Are we good with that? Any questions? Okay. Then the second one is, at what rate is the surface area changing through time? Well, to be able to do that question, I need to find what the surface area is, and it needs to be a function in terms of these 3 variables. Well, the surface area is basically the 4 sides of this cuboid added up. So if you look at the bottom, it's a W times L, but there's a roof and a floor, so that's 2 WLs. If you look at this front panel and this back panel, and they're W times H, and there's 2 of them. And if you do the side panel, they're L times H, but there's a front and the back, so there's 2 of them. Are you comfortable with this formula and where it came from? So if I wanted to find the rate at which the surface area was changing, it would be dA by dL times dL by dt plus dA by dW times dW by dt, and then finish with dA by dH times dH by dt. And I'm going to use the blue ones again, the positive ones. So we are going to do the derivative of this with respect to L. So if you differentiate these terms with respect to L, you're going to get 2W, nothing out of that, plus 2H times 4. If you now differentiate this with respect to W, you're going to get 2L plus 2H plus nothing times 4 again. And I'm going to show you room. If you did the last one with respect to H, you get nothing from that one. You get a 2W plus a 2L times 8. So far, so good. Right. Won't all these W's and H's be 3, 4s, and 8s when I get them from here? And you'll get 212 or 90s, 190 or whatever it might be, and that'll be your answer. Okay, so I'll just leave it there. Now there is a third one, and it's find the diagonal, and that's a sneaky one. Well, you might be thinking, what diagonal are they talking about? Are they talking about the corner on the floor to here and here? Are they talking about the diagonal from this corner to that one? Nope. They're actually talking about the diagonal that goes from here all the way up there, sometimes called the space diagonal. Can you imagine that diagonal that I've just drawn? And I'm going to tell you something just to make your life easy. I'm going to call that distance d, and d squared is length squared plus w squared plus h squared. Does that seem reasonable that the diagonal might be something simple like that? Right. So that diagonal squared, you can do it through using Pythagoras twice, which means that d is going to be this guy. And if you want to find the rate of change of that guy with respect to t, you are going to do exactly the same as we did all the other times. You're going to do a partial derivative with L, dl by dt, plus a partial derivative with W, dw dt, and lastly a partial derivative with respect to H, dH by dt. Now, that one's probably the ugliest of the three that we're going to differentiate. You agree? Isn't this function symmetric? So if I find this answer, can't I make a good prediction on what these two are without having to do it? Right. So if I get the answer to this one, I should be able to figure out using symmetry what this answer is and what this answer is. And that might save you a couple of minutes. It's better than nothing. Are we okay with that question? That's as far as I want to take it, because I want to leave you to do stuff. Okay, I got a nod. I'm good. So we are finished that section and we're moving on to our next section, which is not due this week. So although this next section is not due this week, and it won't be in the test, right? Test number 1 is going to have the 2 sections that we've done, but that's all. I strongly suggest that you do as much homework from this section as you can, so that next week you'll have less work, right? So it's just things never come out exactly perfect. You don't expect me to finish on Friday the exact section. So there's going to be this little, sometimes a little bit more, sometimes a little bit less going on. So we're going to find what's called the directional derivative and a thing called the gradient vector. Okay. The thing that we're going to do, I guess I'm hesitating a lot because I'm trying to figure out a way of phrasing this, because it's a little bit, it's not a little bit, it's a lot of trying to imagine something in 3D when I can only draw it in 2D. And it's not really easy for me to, I'm not the greatest artist in the world, but nonetheless, I'm going to try my best. I want you to imagine that we have got a surface in 3D, right? You know, the kind of, curved piece of surface, right? And that surface is going to have the formula z equals some function of x and y, okay? You can also have it written down like f of x, y, and equals, right? Whatever way you want to write it, but that's what the surface is. Now, on the floor, right, there's going to be a point. So in a directional derivative, you have a point. Let's say it's that point there. That's on the floor. Now, if you take that point on the floor, you then pick a direction to go. And you do the usual way of doing directions is the way we're going to do it, right? You start pointing at the x-axis this way, right? And then you curve anti-clockwise. It's a bit hard to imagine because it's on the floor and it's facing a weird direction. But can you imagine that angle there, right, is theta? Now that dot, if you go up, won't it eventually, it'll touch the surface? And can you imagine we went in that direction, the same direction as below on that surface. So far, so good. Now, I want you to imagine that you cut the surface, right? So imagine the surface was a big cake and you cut the knife in the angle theta, right? So you cut it so that when it hit the bottom, you'd make 30 degrees or whatever the angle is, right? When you do that, what you end up with, miracle if I get it right, can you imagine you'd end up with a curve? You know, that's what your cake would look like side on, right? You will then find the slope of the tangent line at that point. So what I'm trying to tell you is that's what we're going to find. We are going to find this thing called a directional derivative. And God, it is murder. And I don't think I'm being very successful. But you're getting the gist of it. You're going to find the slope of a surface pointing a certain direction at one given point, right? So you pick a point, find the surface, point in a certain direction. Now, analogy might help. Can you imagine that there's a hill? And the point that we're interested in was on the floor, but when you project the point upwards, it touches that bit of the hill. If I go in that direction, would you agree that I'm going quite steep uphill? If I end up going in that direction, couldn't I easily have a slope of 0? And if I walk kind of diagonally this way, couldn't I just as easily have a negative slope? So in a way, isn't directional derivative saying, if you're on a surface and you look in a certain direction and you start walking, what kind of hill are you doing? Are you going uphill? How steep is it, right? Are you just walking along the bend, in which case it's 0? Are you walking downhill if you go in that direction, in which case the slope's negative? Does that help a little bit better, that analogy to what we're finding, right? So we're going to come up with a number, which is the slope of the hill at any given point if you walk in that direction, right? So far, so good. So that's what a gradient, a direction derivative is. What is a gradient vector? Well, if you take any function, f of xy, right? So z equals f of xy. If you take any function like that, the gradient vector will be written with this notation. An upside down capital triangle with an arrow above it, that means it's a gradient. And the gradient, that's what you say out loud, of f. And it's a vector. And it's a partial derivative of f with respect to x, comma, the partial derivative of f with respect to y. And we call that guy the gradient vector. So far, so good? Right. Now, let me just do a couple of finding gradient vectors, right? Not worry about this yet. Just finding some gradients so we get comfortable with them. So if my function was x cubed plus xy squared minus 7, just for argument's sake, then my gradient vector would be the partial derivative with x, comma, the partial derivative with y. And if you differentiate this expression with respect to x, you get 3x squared plus a y squared, and then nothing, comma. If I now differentiate it with respect to y, you get 2xy. Do you notice that the gradient vector is a two-dimensional vector? And do you notice that the components of it, right, the things that it's made of, are a mixture of some formula of x and y typically, right? So that doesn't just have x's in it, and that doesn't have some y's. You see, they both have a bit of x, but both have a bit of y. Make sense? Let's try another one. Suppose I give you a function, and it's e to the sine x cosine y, and I want to find its gradient vector. Now it's a partial derivative with respect to x, the partial derivative with respect to y. If you differentiate this fella, and by the way, that's a multiplication, just looks weird, but it is sine x times cosine y. If you differentiate this with respect to x, it's a chain rule. You get e to the sine x cosine y. Now the tricky part. What is the derivative of sine x cosine y? Because it is essentially a chain rule, and that's what we would call the inside function. So what's the derivative of sine x cosine y with respect to x? Sine x cosine y with respect to x.
Sine y.
Try again. But thanks for trying.
Oh, I had my headphones muted.
Okay, go for it again. Whoever said I had my headphones muted.
Cosine x cosine y.
Correct. Can you see why you need both terms? Because it's basically 5 sine x, and now you're getting 5 cosine x, but the 5 is really cosine y, right? Now, once you've done one of them, it's a little bit easier to do the other one, I think. And so you're going to have e to the sine x cosine y. This time I'm differentiating with respect to y. So if you differentiate sine x cosine y, but with respect to y, you get a negative sine x sine y. And that is how to find a gradient vector. Can you see you're just doing lots of different partial derivatives? So, I mean, partial derivatives is going to be your theme pretty much on and off for the next 10 weeks, right? You're going to differentiate all sorts of things. So far, so good. Any questions? Do you want to see another gradient vector, or can I do the next piece? I need you to tell me. Okay, if you don't tell me, I'm assuming it's good. So next thing I'm going to do, still not there yet, is I'm going to tell you how to find a unit vector given the angle theta that it makes at the origin. So if I tell you this guy here, right, goes like that, and I make a unit vector, I make that guy 1, how can I find what this unit vector is? And I'm going to call the unit vector U for unit vector. Somewhere in your math career, you will remember, I hope, the x component and the y component of a vector when you know the radius and you know the angle. The x is r cos theta, agreed, and the y is r sin theta. Do you remember those two guys? X is r cos theta, y is r sin theta. Somewhere you have me. Okay, in this case, since the radius is 1, doesn't the x end up just being cosine theta? And the y ends up being sin theta. So a unit vector that makes an angle theta with the x-axis has components. The x component is cosine theta, and the y component is sin theta. Are you comfortable with what I just did there? Just it's very general. That if you want a unit vector pointing in a certain direction, so it makes an angle theta with the x and y axis, as it does here, and that it's 1 unit long, then its x component is this number and its y component is that. So for instance, if theta was pi upon 4, right? So if the angle was pi upon 4, the unit vector that would make that work would be the cosine of pi upon 4, comma, the sine of pi upon 4. and you get a hold of, have I got one handy? I think I do, yeah. You get a hold of a unit circle and you say, oh yeah, is it the cosine of pi upon 4 root 2 upon 2? And the sine of pi upon 4, it's just also happens to be root 2 upon 2. Well, suppose theta was 2/3 pi, right? Suppose the angle was up here somewhere. What would the unit vector look like in this case? Well, it would be the cosine of 2/3 pi and the sine of 2/3 pi. And so if you thought that the unit circle had left a building and you can just forget about trig, sorry, nothing ever leaves a building in math. So I'm looking at the cosine of 2/3, which is here, right? And there's your guys. Is it the x or the y coordinate that is the cosine here?
The x.
Okay, so it's -1/2 in this case. And isn't the y component then the sine? And the good news is, do you notice that that coordinate is essentially the same thing as the vector? You see, it's the same two numbers in the same order. And because technically that vector, that coordinate could be thought of as what's called a position vector, which means it's the same thing, right? We've done that in Calc 3, right? The position vectors are essentially telling you the same thing as coordinates. Where we're doing it the other way around, coordinates are telling me position vectors. So if I told you an angle theta, and as long as it's in the unit circle, are you comfortable you could find the unit vector that would behave like it? Okay, so that's that little piece. We need all these little pieces before we can actually do the question, which is this fella. So let's show you our first example of a directional derivative question. And that way I can also give you some of the notation, i.e. the way that we write it. So I'm going to do a version of question 1. And the surface that we're going to use is this one here. So it's xy cubed take away x squared. We're interested in the point 1, 4. So that's going to be the point that gets projected up to the surface. And the angle that we're going to travel once we reach that hill. So we go up till we find where it is on the hill, and then we point at pi upon 3. What does the directional derivative look like? So here is the notation. You do a big capital D, you do a little baby vector u, and then you put the value of the function f. And in this case, since we're interested in the point 1, 4, you put in 1, 4. So you would read this out loud as the directional derivative of f at the point 1, 4. So that's the directional derivative of f at the point 1, 4. So can you imagine that's where my finger is on the surface, and we're pointing at pi upon 3, which let's pretend it's that one in the middle. We are going to find whether I'm going uphill, positive slope, whether I'm going downhill, or whether I just happen to be going around the center of the hill, whatever it might be at that given point. And there is a formula for it. And you might be surprised at what the formula is. Can you remember dot products? Well, guess what? It's the dot product of the gradient vector evaluated at 1, 4 dot the unit vector of the angle. Now, haven't we already dealt with both of these? Can you see why why we're doing it the way it is? So let's take a side back. We'll come back to this little squiggly line. Let's find the gradient part of the answer. So that's the original function. The gradient of f is partial derivative with x, comma, partial derivative with y. Differentiate this guy with respect to x, and you get y cubed, take away 2x. Differentiate this guy with respect to y, and you get 3xy squared. So far, so good. Comfortable with this? Right. We're now going to evaluate the gradient vector, and we're going to evaluate it at the point 1, 4. So that's 1, and this is 4. So what does that get me? It gets me 4 cubed, take away 2 times 1, comma, 3 times 1 times 4 squared. Okay, that's 64, take away 2, so that's 62. And that's 16 times 3, which is 48. Hopefully I got that right. So this guy here is 64, comma, 48. Dot product. Okay, let's take the shortcut. Pi upon 3 on my unit circle makes my life easy. Pi upon 3 is this one here. Can you see it? This one here. Okay. So the unit vector that points in that direction is 1/2 root 3 upon 2.
Sorry, isn't it supposed to be 62, 48?
Can I not count? What did I do? Oh God, yes. Well caught. 62, 48. We're happy about this guy? Okay, now you could just turn them into decimals and call it good, but they want the exact value, so we're going to have to stick to it. So the dot product is 62 times 1/2 plus 48 times root 3 upon 2. So that guy gets me 31, and that guy gets me 24 root 3. And so the directional derivative of this function at the point 1, 4, going in the direction pi upon 3, ends up being that number. That's pretty big number, would you agree? So if you looked at that surface, wouldn't it be really steep? It'd be like you're on the side of Mount Everest, right? And you're going up, maybe at a slight angle, but the angle you're going up has a slope that's this big. Right. If that had been negative, because it could be a negative number, wouldn't that be I'm going downhill, right? I'm on, the, whatever you call it, I'm on the surface of Mount Everest, but I'm now walking downhill, trying to. If it was 0, wouldn't that be, I'd be at the part of Mount Everest where I'm kind of walking around the band of it, right? I'm not going up, I'm not going down, I'm kind of going horizontally. And so the directional derivative in that case would be 0, which means there's no increase or decrease, at least if you travel in that particular direction. Any questions? I'm going to do more of these, but any questions right now about that process?
The value of u that you used was theta, right?
Yeah, I got this guy, right, from here. So pi upon 3, I got it from here. So essentially the cosine of pi upon 3 and the sine of pi upon 3. But if you look at that, isn't that just the same as the coordinates? So I'm just making my life easy by recognizing that shortcut.
Yeah,
on the unit circle, we are good. So far so good. So let's see if we can find another hill to climb up or down. Which one are we doing this time? Well, I can't really change these too much, but I will do my best. So here we have a function f of x, y, and it's going to be, what's it going to be? It's going to be the square root of x squared plus y squared. And it's going to be at the point, I don't know, 3, 1. And the angle that we're going to go is negative pi upon 6. So I need to find the gradient at that point, and I need to know the unit vector that's the same as traveling in that direction. I'm going to do a slightly different order. Let's get the unit vector first. I know I don't have negative pi upon 6 on my calculator, but or on my sheet of paper here, but hopefully you all know what that's the equivalent to. In the unit circle, what is negative pi over 6 the same angle as?
11 pi divided by 6.
Are you all comfortable about that? You all see what you did there, right? Now, if you go to 11.6, can't we just use the shortcut that that's going to be the x and that's going to be the y? Or if you want to be precise, the cosine of 11.6 pi goes here and the sine of 11.6 pi goes there, which would get you exactly the same numbers. So I want to do that one first, get it out of the way. Put a little bubble so I remember what it is. Now I'm going to do the gradient of the function. Is there anything I should rewrite? Is there another way I should rewrite this to make my life easier?
The 1/2 power.
Okay, so have you noticed that a lot in math, there's a lot of duplication, a lot of the same thing happens in different places and you just get used to doing it. So you, in a way, you sometimes don't even think about it anymore. You just do it because you know that's what you have to do. So here we go. With the partial derivative with x, partial derivative with y. Would you agree that this is a symmetric function? So wouldn't that maybe reduce my workload a little bit, right? Every little bit that you can save is worth it. So here goes. If you multiply by the power, and then you reduce the power by 1, and then you remember that it's a chain rule, so you then finish with differentiating the inside, which gets me 2x. What I end up with is an x, a half power on the bottom, which I'm now going to write as the square root of x squared plus y squared. Are you comfortable with what I did there in like one go rather than two? Right? Half times 2 gets me x. Bring it downstairs and make it a square root. Aren't we using the usual rules of style point? Make me look like the original, right? The original had square roots, so I want square roots. Right. Oh, does anybody know what that surface looks like? Just curious.
Hemisphere.
Oh, yeah, like in half a circle or half a sphere. Yeah, I can see why you think that. It's actually a cone. But you know, you don't need to know that to do that question. I just thought I'd ask. Right, since it's got symmetry to it, do you want to tell me what this answer is without me having to do it from scratch? Not that it's that hard to do from scratch, but what is it anyway?
Put a y over the square root of x squared plus y squared.
Yeah. Okay, you've probably saved yourself, what, 5 seconds, but it's something. Well, that's the general gradient, right? But aren't we interested in this particular one? So I'm going to find the gradient at the point 3, 1. So that's going to be 3 over the square root of 10, and that's going to be 1 over the square root of 10. We're comfortable with where those numbers came from. Right? 3 over 3 squared plus 1, which is where the 10 is, and 1 over 3 squared plus 1. Well, you put the package together, and we can now get the directional derivative of the function at the point 3, 1. It's the dot product, of the gradient with the unit verb. And that gets me 3 root 10, 1 over root 10, dot product with root 3 over 2, negative 1/2. Everybody comfortable with that? No problems? Okay, so that guy times that guy is not nice. No way in the world is it's nice. I get 3 root 3 over 2 root 10, and that guy times that guy gets me negative 1 over 2 root 10. I think the only thing I'm really worried about is probably at least making it a single fraction. Would you agree that's stale points? That's not perfect, but isn't it a little bit better? Just a little. Now, if you've been really fussy, which I don't think web sign is, and to be honest, I don't think I would be either. And couldn't you rationalize the denominator by multiplying the top by root 10 and the bottom by root 10? Can you trust me? It's just as ugly. I mean, it doesn't really bring much to the party. That's why I'm not too worried about it. Matthew, you got a question or are you good?
I was just saying a thumbs up because yeah,
Yeah.
that sounds.
Yeah, seems reasonable. I mean, sometimes it's worth doing, in which case I would push it, and other times you can tell it's not going to do any good, so I don't. I guess a natural pause point for a minute. You might not have a good visual impression, but watch some videos where people can do animations and graphics. I mean, if you're the kind of person that needs to see what you're doing, that would be a good idea, right? I'm just doing the math of it. And that's fine, right? Because at least you know how to get the answer. If you want to visualize it, that's even better. But can you do it is kind of where we are right now. So I think I have time for just one last one. So I might as well pick my own because I can. Right, so we're going to have a function and it's going to be x squared take away y cubed. We're interested at the point 1, 1, and we want to go in the angle pi upon 2. And I hope this comes out to be weird. I don't know, but I'm trying to make it so it's weird, right? Because weird can happen. Okay, so in this particular case, in no particular order, I'm going to find a unit vector that's equivalent to an angle of pi upon 2. And would you agree it's a very simple vector? Okay, and now I'm going to do the gradient. And partial derivative with x, partial derivative with y, and the partial derivative with respect to is 2x, good. And the partial derivative with respect to y is -3y squared. Can I change that to 1, 0? I told you I wanted a weird answer, so it's not changing anything I've done, right? Because I haven't used that yet. And so we have that fella. And so if you find it at 1, 0, you get 2 times 1 is 2, and that gets you 0. And so the directional derivative of f at the point 1, 0 is the dot product of the gradient at 1, 0 with the unit vector in that direction. And so we are looking at a 2, 0 dot 0, 1. And now I've got what I think is kind of interesting, which is what I was aiming for. So in this particular question, right, this particular surface, the directional derivative is 0. Doesn't that mean you're not going uphill, you're not going downhill, you're just kind of walking around the shape without changing your height, right? So you're not going up and you're not going down. You're kind of just walking along, you know, like I had a belt and you're walking along the belt. I think that's a good place to kind of finish on. So Maggie was asking for jokes in my other class. So since I have a few minutes, while you're writing down your last name, we'll do the mummy jokes. You ready? Okay. Which one will I do first? Mia, can you remember the mummy jokes?
The what?
The mummy jokes. Can you remember them?
No.
What about you, Wendell? Can you remember them? No, so they're really forgetful. Good, that means these might actually be new to you then. Okay, mummy, I'm tired of running round in circles. Oh, shut up or I'll nail your other foot to the floor. Mummy, oh, don't you shake your head, Fred. That's good. Mummy, I don't want to go to Australia. Oh, shut up and keep swimming. Mummy, Dad has just gone out. Well, throw some more gasoline on them. Do you remember them now, Wendell?
It sounds familiar, but I still can't remember it.
Okay. I was thinking maybe you blotted those jokes out because they were so painful that your brain decided to protect you. Mia, do you remember them?
No,
No. Are they still bad?
I thought they were good.
Oh, okay. Right. Well, that works.
I do remember them, and I
Okay.
think coming from a teacher, it's pretty funny.
What the mummies are?
Yeah.
Well, you know, Scottish humour tends to be cruel, so we like nobody, no children or husbands get killed in the making of that joke. By the way, just to cover myself. Okay, bye bye, guys. I shall see you all tomorrow, where we get to do a different way of calculating directional derivatives.